record a very quick video about the direction of force on charge carriers. I've been motivated by this picture. This is a bubble track image showing the trajectories of both positive and negative charges within a bubble chamber. Okay, so these could be anything from protons to electrons to different quarks. Doesn't really matter. The key idea here being that in the magnetic field, they've been deflected in different directions. And that's the kind of key point for today. And the reason I brought this up is because I've been looking through some past paper questions, and a lot of the past paper questions are kind of a bit unfair. What they tend to do is consider the effect of the magnetic field on a negative charge. Why is this not fair? Well, when we use the left-hand rule, there is an assumption, and that assumption is that the current is conventional current, i.e. it is caused by positive charge carriers, for example, protons. Okay, now the reason I've highlighted those words, positive charge carriers, in red, is because that's what you can see on the diagram here. Here we've got a field into the page, and if we look at that V arrow, which is very small, that would be the direction of the current. So the current is up. If you're using your left-hand rule, which hopefully you are familiar with by now, you should be able to see that if we put our finger into the page, our middle finger very rudely up, then you will get a force from your thumb, which is pointing to the left. Okay, and so this case, that shows me that the force on those particles would be positioned at that point would be to the left, and that would be the left-hand circle you can see there, the red one, doing a kind of anti-clockwise loop. So if my charge carrier was a proton, it would follow the left-hand circle. It goes without saying then that the negative charge carrier, for example, an electron, would do the opposite. It would experience a force in the opposite direction. Now this often presents quite an issue for science teachers because there's a lot of rules going on, okay, and it gets quite confusing for students. Now, as a student of physics, you do have a couple of options here. One of them would be to use a kind of modified version of Fleming's left-hand rule, which is actually called the right-hand rule. Okay, but I find that gets quite confusing for students because it's too many rules. We've already got a right-hand rule. Okay, we've already got a rule which in place, and I think the following advice is the best. This is what I would go for. If you are considering the force on a charge carrier, what I would do is use the left-hand rule. So in sense, actually, what I would do initially is ignore the charge. Simply use the left-hand rule. Okay, so if you've got current, don't worry about whether that is current due to positive or negative charges. Just think about the direction of the current using your second finger. Okay, and then use that to determine a force. I would then recheck the question. And if the charge is negative, then simply reverse the force direction. So just like we've done in this question, okay, if we had field going into the page, current going up, that's the green arrow, then my force would be to the left. Now, if I was considering a negative charge, all I'd have to do is say, well, whatever a negative charge does is the opposite to a positive, and so therefore the force is going to be not to the left, but to the right. Now, I appreciate that that can be quite vague and a bit waffly. However, I do find that students tend to like the idea that whatever a positive charge does is going to be opposite for a negative charge. And as long as you remember that, you should be okay. I appreciate this seems like quite a small point. However, I've noticed it comes up in quite a lot of multiple choice questions, particularly for IB physics. It comes up quite a lot, and so often when students think they've got the right answer, for example, they find that the force is to the right, they're disappointed when they find that actually the force is to the left. And that's because actually the question has considered a negative charge, and all that they've learned so far has been relative to positive charges. Okay, so just have a think about that, and whilst you're doing questions on magnetic force and charge, try to sort of square that in your brains. And as ever, please let me know if there's anything which is a bit confusing there. Thanks for watching. And yeah, let me know if there's anything I can clear up there.